NEC Article 430.21 dictates the sizing of motor circuit conductors, stipulating that they must be rated at least 125% of the motor's full load amps, or FLA. Considering a 3 horsepower motor operating at 230 volts, 3-phase, 60 Hz, with a rated FLA of 9.6 amps, the calculation unfolds as follows. 9.6 amps multiplied by 1.25 equals 12 amps. This calculation suggests that a number 14 American wire gauge, or AUG, conductor, rated for 12 amps appears suitable according to Article 430.21. However, Rule 310.1516 introduces another layer of consideration. This rule imposes limitations on the overcurrent protection for conductors marked with an obelisk such as number 14 THHN copper, stipulating that it should not surpass 15 amps. This presents a conflict. Article 430.21 centers specifically on motor circuit conductors, permitting a 125% multiplier for FLA. Conversely, Rule 310.1516 adopts a broader approach, lacking explicit exclusions for motor circuit conductors. In situations involving conflicting rules, the more specific requirement takes precedence. Therefore, Article 430.21's mandate governs the selection of motor circuit conductors. Now let's delve into the nuances of conductor ampacity and the implications of exceeding ampacity limits. The ampacity of a conductor refers to its current carrying capacity, typically expressed in amps. Exceeding this limit can lead to several detrimental effects. Firstly, overheating occurs as the conductor's temperature rises due to excessive current flow. This elevated temperature can degrade the insulation surrounding the conductor, leading to premature failure and increased risk of short circuits or ground faults. Secondly, voltage drop becomes more pronounced as the current increases. This voltage drop can impair the performance of the motor and other connected equipment, potentially causing them to operate inefficiently or fail altogether. Thirdly, the lifespan of the conductor diminishes as it is subjected to thermal stress and insulation degradation. Over time, the conductor's ability to safely carry current decreases, increasing the likelihood of failure. Moreover, exceeding the ampacity limits can create hazardous conditions, including the risk of fire. Overheated conductors can ignite surrounding materials, posing a significant safety threat. Therefore, it is crucial to adhere to ampacity ratings specified in the NEC and select conductors that are adequately sized for the intended application. In cases where the calculated current exceeds the ampacity of a particular conductor size, it is necessary to upsize to a larger conductor with a higher ampacity rating. This ensures that the conductor can safely handle the anticipated current load without overheating or experiencing excessive voltage drop. Now let's discuss the correct wire size selection based on NEC guidelines. In this particular scenario, the calculated current of 12 amps necessitates the use of number 12 AWG wire. Although number 14 AWG wire may initially appear adequate based on the 125% multiplier for FLA, Rule 310.1516 imposes a more stringent limitation on overcurrent protection. Therefore, to comply with NEC regulations and ensure safe operation, number 12 AWG wire is the appropriate choice. This selection provides sufficient ampacity to handle the calculated current load while adhering to the overcurrent protection requirements outlined in the NEC. Furthermore, it is essential to consider other factors that may influence wire size selection, such as ambient temperature, conductor bundling, and conduit fill. High ambient temperatures can reduce the ampacity of conductors, requiring the use of larger wire sizes to compensate for the dilating effect. Similarly, bundling multiple conductors together in a confined space can also reduce their ampacity, necessitating adjustments to wire size. Conduit fill refers to the percentage of the conduit's cross-sectional area occupied by conductors. Exceeding the maximum allowable conduit fill can impede heat dissipation and reduce the ampacity of the conductors. Therefore, it is crucial to consider these factors and consult the appropriate NEC tables and guidelines to ensure that the selected wire size is suitable for the specific installation conditions. Now let's explore the significance of NEC Article 430 in detail. NEC Article 430 provides comprehensive guidelines for the installation and protection of motors, motor circuits, and motor control equipment. It covers a wide range of topics, including motor circuit conductors, motor overcurrent protection, motor disconnecting means, and motor control circuits. Understanding the provisions of Article 430 is essential for ensuring the safe and reliable operation of motor-driven equipment. Article 430 addresses various aspects of motor circuit conductor sizing, including the calculation of minimum conductor ampacity, the selection of appropriate conductor types, and the requirements for overcurrent protection. It specifies that motor circuit conductors must have an ampacity not less than 125% of the motor's full load current rating, as determined from the motor nameplate or applicable NEC tables. This requirement ensures that the conductors can safely handle the continuous current load of the motor without overheating or experiencing excessive voltage drop. Article 430 also addresses the selection of overcurrent protection devices for motor circuits. It specifies that motor overcurrent protection devices must be sized to protect the motor against overload and short-circuit conditions. The size of the overcurrent protection device is typically based on the motor's full load current rating and the type of motor. Article 430 provides detailed guidelines for determining the appropriate size of fuses, circuit breakers, and other overcurrent protection devices for motor circuits. In addition to conductor sizing and overcurrent protection, Article 430 also covers the requirements for motor disconnecting means. It specifies that each motor must have a disconnecting means that is readily accessible and capable of disconnecting the motor from all sources of power. The disconnecting means must be rated to safely interrupt the motor's full load current and locked in the open position during maintenance or repair. Furthermore, Article 430 addresses the requirements for motor control circuits, including the wiring, overcurrent protection, and disconnecting means for motor starters, controllers, and other control devices. It specifies that motor control circuits must be designed and installed to minimize the risk of accidental starting and to provide adequate protection against electrical hazards. Now, let's discuss the implications of Rule 310.1516 in greater detail. Rule 310.1516 specifies the allowable ampacities for insulated conductors rated up to 600 volts. It provides a table of ampacities for various conductor sizes and insulation types, based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit and no more than 3 current carrying conductors in a raceway or cable. The ampacities listed in Table 310.1516 are based on the conductor's ability to dissipate heat and maintain its insulation within safe temperature limits. Exceeding the ampacity limit specified in Table 310.1516 can lead to overheating, insulation degradation, and increased risk of electrical hazards. Rule 310.1516 also includes notes that provide guidance on adjusting ampacities for different ambient temperatures and the number of current carrying conductors in a raceway or cable. These adjustment factors are necessary to account for the effects of temperature and conductor bundling on the conductor's ability to dissipate heat. In cases where the ambient temperature exceeds 30 degrees Celsius, the ampacity of the conductor must be derated using the appropriate temperature correction factor. Similarly, in cases where more than 3 current carrying conductors are installed in a raceway or cable, the ampacity of each conductor must be derated using the appropriate adjustment factor. These derating factors ensure that the conductors are not subjected to excessive heat and that their insulation remains within safe temperature limits. Rule 310.1516 also specifies the requirements for conductor identification. It states that conductors must be clearly identified by color coding or other means to indicate their function. This helps to prevent accidental miswiring and ensures that electrical systems are properly installed and maintained. Furthermore, Rule 310.1516 addresses the requirements for conductor terminations. It specifies that conductor terminations must be made in a manner that ensures a reliable electrical connection and prevents the conductor from being damaged or stressed. Conductor terminations must be properly tightened and insulated to prevent corrosion, loosening, and electrical hazards. Now, let's explore the importance of conflict resolution in the NEC. The NEC is a comprehensive document that covers a wide range of electrical installation practices. However, due to the complexity of electrical systems and the diverse range of applications, conflicts can sometimes arise between different sections of the code. In cases where conflicts occur, it is essential to apply sound engineering judgment and consult the appropriate authorities to resolve the conflict and ensure that the installation meets the intent of the code. The NEC provides guidance on resolving conflicts between different sections of the code. It states that where there is a conflict between a general requirement and a specific requirement, the specific requirement shall apply. This means that if a particular section of the code addresses a specific situation or application, its requirements take precedence over the general requirements that apply to all installations. However, in cases where the conflict is not easily resolved, it may be necessary to consult with a qualified electrical inspector, engineer, or other expert to determine the appropriate course of action. These experts can provide valuable insights and guidance based on their knowledge and experience with electrical codes and standards. Furthermore, it is important to document any conflicts that arise and the steps taken to resolve them. This documentation can be helpful in the future if similar conflicts occur and can also provide valuable feedback for future editions of the NEC. The NEC is a living document that is constantly evolving to address new technologies and installation practices. By documenting conflicts and providing feedback, electrical professionals can help to improve the clarity and effectiveness of the code and ensure that it continues to provide a safe and reliable framework for electrical installations. Now let's discuss the significance of selecting the correct wire size. Selecting the correct wire size is crucial for ensuring the safe and reliable operation of electrical systems. Undersized wires can overheat, causing insulation damage, voltage drop, and potentially leading to fire hazards. Oversized wires, on the other hand, can be more expensive and may not be necessary for the application. The correct wire size is determined by several factors, including the amount of current the wire will carry, the length of the wire, the ambient temperature, and the type of insulation. The NEC provides tables and guidelines for determining the appropriate wire size based on these factors. When selecting wire size, it is important to consider the continuous load current, which is the maximum current that the wire will carry for an extended period of time. The wire must be sized to carry at least 125% of the continuous load current to prevent overheating. It is also important to consider the voltage drop in the wire, which is the decrease in voltage that occurs as current flows through the wire. Excessive voltage drop can cause equipment to operate inefficiently or not at all. The NEC provides guidelines for limiting voltage drop to acceptable levels. In addition to current carrying capacity and voltage drop, it is also important to consider the ambient temperature when selecting wire size. High ambient temperatures can reduce the ampacity of the wire, so it may be necessary to use a larger wire size to compensate for the temperature derating. Finally, it is important to select a wire with the appropriate insulation type for the application. Different insulation types have different temperature ratings and resistance to moisture, chemicals, and other environmental factors. The NEC provides guidelines for selecting the appropriate insulation type based on the application. By carefully considering all of these factors, electrical professionals can select the correct wire size and ensure the safe and reliable operation of electrical systems. Now, let's conclude with a summary of the key points discussed. In summary, the selection of motor circuit conductors requires careful consideration of NEC guidelines, particularly Article 430.21 and Rule 310.1516. While Article 430.21 permits a 125% multiplier for FLA, Rule 310.1516 imposes limitations on overcurrent protection for certain conductor types. In cases of conflict, the more specific requirement of Article 430.21 takes precedence. Therefore, for a 3 horsepower motor with an FLA of 9.6 amps, the correct wire size is number 12 AWG to ensure compliance with NEC regulations and safe operation. Additionally, it is essential to consider other factors such as ambient temperature, conductor bundling, and conduit fill when selecting wire size. These factors can affect the ampacity of the conductors and may require adjustments to wire size to ensure safe and reliable operation. By adhering to NEC guidelines and considering all relevant factors, electrical professionals can ensure that motor circuits are properly designed and installed to meet the demands of the application while maintaining safety and reliability.